Welcome to the TWIML AI podcast. I'm your host, Sam Charrington. All right, everyone. I am on the line with Ilias Diakonikolas. Ilias is on the faculty at the University of Wisconsin-Madison. Ilias, welcome to the TWIML AI podcast.
Great to be here, Sam.
I'm really looking forward to diving into our discussion. Before we do, I'd love to hear a little bit about your background. Your primary research interests are in algorithms and machine learning. And if the paper that we're going to discuss this time around, distribution independent pack learning of Halfspaces with Massart Noise, which won the Outstanding Paper Award at NeurIPS. If it's any indication, your work is quite theoretical in nature. Tell us a little about your background and how you came to working on this type of work.
Right. So I grew up in Greece. This is where I did my undergrad. I moved to Columbia University for grad school. My grad school was in a topic called theoretical computer science. So I'm an algorithms person. And somehow in the process, I realized that the best way to have an impact in the world, if you're doing theoretical algorithmic research, is to actually work on algorithmic questions that come from machine learning and statistics.
And why is that? Why is that the best place?
I mean, maybe the phrasing is not accurate. I think it's really a good place because this is a setting where this is.
I think our listeners would all agree, but I'm curious your thought on it.
So I actually started doing this before it was popular, because I could really see that maybe not all of the theoretical algorithm that one develops, but maybe some of them could be used in practice, and you could see the sort of practical improvements in data analysis tasks. So in particular, I used to like doing theoretical algorithmic research just for the sake of doing it. But sort of later, like after I finished my PhD, I started gravitating towards theoretical questions that, if solved, would actually have a practical impact.
Describe for us broadly your research interests and focus so that we have a little bit of the context out of which this paper comes.
So, I mean, I have broad interests within algorithms and machine learning. So this particular NeurIPS paper belongs at a high level in an area which is called high-dimensional robust learning. The idea here is that historically, every machine learning algorithm needs to make some assumptions, assumptions about the model where the data comes from. So in some sense, very roughly speaking, every algorithm could be viewed as a data fitting method. You're trying to fit the data to a model. Now the issue is that this assumption about the data coming from a model of a given type is very crucial. So, and typically you do not want your algorithm to overfit to this assumption, in the sense that if this assumption is not exactly true, but if it's approximately true, you want your algorithm to still work. And unfortunately, in high-dimensional settings, we realized about 5 years ago that this is actually not the case. Even a very tiny deviation from the assumed model could make the machine learning algorithm very, very fragile. So we started and decided that, okay, we need to rectify this and develop a methodology to have robust learning algorithms for high-dimensional problems.
And so when you talk about high-dimensional problems and perturbations, are you thinking about things like the adversarial examples types of problems that we are familiar with, where you've got an image, high-dimensional, and you apply some noise to it?
So that's a great question. I was expecting this question exactly to draw a difference. So these types of adversarial examples, they're also some type of robustness. They require some type of robustness, but it's somewhat different than the one I'd like to discuss. In particular, in the sort of adversarial robust setting, what you have is that you train you train your neural network on some images, right? And then you perturb those images in a way that's imperceptible to humans, and see how the model you learned performs. We have learned that it's actually non-robust, and we need to do something to make it robust. So the perturbations in the adversarial robust setting take place at test time. So you train with a bunch of clean data, and then you want to test on a set of corrupted data. So the setting of robustness that I care about, at least with respect to this line of work, is something that's called test time attacks, where you actually train on corrupted data.
Mm-hmm.
Okay, so these two are related. So these two notions of robustness are related, but they're also quite a bit different.
And you said they're called test time
Yeah,
attacks, but the data is perturbed in training?
so adversarial examples are called test time attacks.
Oh, got it. Got it.
What I'm going to talk about is called training time attacks.
Got it. Okay.
Right? So let me give you an example. Okay, like the most basic example that I expect anyone could understand with just a little bit of background. So if I give you samples, like IID samples, from a probability distribution, like a Gaussian, and I ask you to find the expectation, the mean value of the distribution where the samples come from, let's say in one dimension, then what would you do?
To find the mean value,
Yeah.
you'd sum them and divide by the number of samples you have.
Yeah, that's fantastic. That's called sort of empirical mean, and we know that it works, right? Unfortunately, though, if one of the samples that I give you is not drawn from the distribution that you assumed it was, it's an
Mm-hmm.
outlier, then the average doesn't work anymore.
Right.
Because the average could be arbitrarily far from the true mean. It's not going to converge to the true mean, even if you take infinitely many samples.
Mm-hmm.
So what do we do in this case? So for the one-dimensional setting, the solution is known for, like, I don't know, a century in statistics. So instead of taking the average, you're taking something which is called the median.
Mm-hmm.
Okay, so we know that the median is robust to outliers, and it's optimally robust for one-dimensional problems. Right? Now imagine a generalization of this problem to high dimensions. So now instead of observing one-dimensional points, you're observing high-dimensional points. Every observation that you have is a high-dimensional vector, let's say in a million dimensions. And you want to do the same thing. You want to actually compute the expected value of the corresponding distribution. Now, in the case of clean data, you would do exactly the same thing that you did in the one-dimensional case. You would sum all the samples and then divide by the number of the samples. So this is the empirical mean in high dimensions. And in the
Mm-hmm.
case of clean data, it works. Now, the difficulty is actually generalizing this high-dimensional empirical mean when you actually have, let's say, 10% of your samples being arbitrary outliers. In this case, unfortunately, there is not such an easy solution as taking the median.
Meaning because the median in a high dimensional scenario isn't well defined, or because of the number of outliers you have?
These are great questions. So there are many ways to define a notion of a median in high dimensions. For example, one thing that you could do is look at every coordinate individually and calculating the median of every coordinate and giving that answer.
Mm-hmm.
Unfortunately, this is not going to work. The reason it's not going to work is because you have many dimensions, and in some sense, the noise can accumulate across the dimensions. So if you have, let's say, even a 1% of outliers, then the error you're going to get at the end is going to be very large in the worst case. It would actually it would actually scale with the number of dimensions. And this is something that you can avoid. We know that you can avoid that if you look at like information theoretic bounds, but we didn't know how to avoid it with a computationally efficient algorithm, with a method that you can actually run. Right? So what we did 4 years ago with a number of great co-authors is we developed the first method that is actually robust for estimating the mean of a high dimensional distribution to a constant number of outliers. So even if you have, let's say, 20% of outliers, and no matter how high the dimension is, the algorithm runs efficiently and gives you an accurate approximation of the mean.
What's the general flavor or shape of this algorithm?
I see. So there are many versions. Maybe the easiest one is about sort of detecting and removing the consequential outliers. So we are in a high dimensional setting. So the most sort of naive thing to try to do is detect the outliers and remove them,
Mm-hmm.
right? And after you do that, then you just output the mean of the rest. Right? It will be the ideal methodology to solve the problem. The issue is that this is impossible. We can prove that it is impossible to actually detect the outliers in a high dimensional setting. So what we do So the next thing to try to do is, okay, maybe I cannot detect and remove all the outliers. Maybe I can detect and remove the ones that if I kept in the data set, then they would actually skew the empirical mean by a lot. And it turns out that this is something that you can do by using spectral method. So I guess I do not have like a picture to show you, but the idea is this, that let's say that your data set is some kind of cloud in high dimension. Imagine it like a sphere, right? If an outlier is very far from that sphere, then you can eyeball it. You can eyeball it and you can remove it. These are outliers that are very easy to remove. Unfortunately, in high dimensional settings, these are not the outliers that can kill you. These are not the only outliers that can kill you. There can be outliers that are within the initial cloud of points. Each one of them individually looks like a fine point. You cannot say that this, on its own is an outlier, but somehow the outliers have the ability to collude with each other to skew your estimates. So what you need to do is somehow detect outliers in a high-dimensional setting in a more global scale. So it's like a local versus global type of phenomenon that appears here, and this is because of the high-dimensional setting.
Now, does your problem presume single prior distribution? I'm thinking about the one-dimensional example where, as opposed to trying to identify and discard outliers, you might have multiple prior distributions and you're trying to determine which of your samples belongs to which distribution as a way to formulate the problem.
Right. So, okay, so the formulation that we use in this setting is a frequentist formulation. It is not a Bayesian formulation. So there is no such thing as a prior. So what we really assume is that we have a family of distributions, let's say a family of models, where we assume the clean data comes from. Let's say, for example, the clean data could come from a mixture of high-dimensional Gaussians. So that's our assumption.
Okay, so you do assume a mixture of Gaussians as opposed to a single Gaussian.
Yeah, we can do that. And in
Got
fact, there are many different assumptions that we can handle algorithmically. These are related, this is a technical term, so these are related to the rate of increase of the moments of the distribution of the good data. So if the moments of the good distribution behave well in a technical sense, we can actually solve the problem. But what I want to emphasize is that some types of assumptions of this form are actually necessary, in the sense that if you make no assumptions about your good data in this unsupervised learning, where you have unlabeled data, the problem is not solvable even information theoretically, even like with infinitely many samples. And the reason is that the outliers, they have the ability to actually completely mask the information that's contained in the good data.
hmm
So some type of assumption like the one that you alluded to is actually information theoretically necessary.
Got it.
Right, so this is so basically where sort of things started, and this is an unsupervised setting. Unsupervised in machine learning means that the data set that you observe is an unlabeled data set. You have a bunch of points in high dimension without labels. So maybe it's time for me to move to the NeurIPS paper.
Yeah. Yeah. So
Right.
where does that paper come in?
Right. So this is a supervised learning setting. This is a setting where you observe labeled data. And what you're trying to do is you're trying to fit a linear model. This is like the most basic family of concepts that you could try to fit to the data. Like literally a linear separator. You're trying to find a linear separator that separates a point into two classes, the positive points and the negative points. Okay, this seems like almost like a too simplistic problem, and indeed, in the case of clean data, it is. Now, the question is what happens when the labels that you observe are actually not clean. They have, let's say, some kind of random noise attached to them. Can you still recover the true linear model efficiently in the presence of these types of corruptions? And what we show in this paper is that, in fact, in a very reasonable model of random label perturbations, this is something that can be done. It can be done with a computationally efficient algorithm.
If I understand what you're saying, it's that a linear model is insufficient in the case of clean data, but when noise is added, that a linear model, a simple model, becomes sufficient.
Let me rephrase. So the reason that we consider settings where the labels are noisy is because these settings are more realistic in practice. We cannot really assume that we observe labeled data and our labels are perfectly clean. So what I was trying to say is that if you make the unrealistic assumption that the data is clean, then we knew how to fit linear models since the 60s. Okay? What we did is we gave an algorithm to fit linear models under the more realistic assumption that the labels are actually randomly perturbed. So this is the contribution of this work compared to prior works. That we can actually learn linear separators efficiently in the presence of noise.
And so the paper is called Distribution Independent Pack Learning of Halfspaces with Massart Noise. There's a bunch of terminology in there. Walk us through that terminology: pack learning, half-spaces, Massart Noise. Where do they come into play?
Okay, that's great. Right, so pack learning. So pack is an acronym. It means probably approximately correct. Is a standard model of binary classification introduced by Leslie Valiant in the 80s, and even before that, similar models existed by Vapnik. So basically, the model is essentially for someone who has seen statistics and machine learning, the most natural thing you could imagine, that you observe a bunch of IID labeled examples that come from a distribution on points with corresponding labels, and then you're trying to find a classifier that generalizes over unseen data.
Mm-hmm.
All right, so that's the definition of the pack model. Now, the term distribution independent, which in fact maybe is in some sense unnecessary, because the original definition of the pack model was distribution independent, is that I'm going to observe a bunch of labeled examples x and y. Okay, x is going to be my point in high dimensions, and y is going to be a binary label, 0 or 1. So what I do not want to do is I do not want to make any assumptions about the distribution of the x's. Right? I do not want to assume that the x's are drawn, let's say, from a Gaussian distribution. So the only thing I'm going to assume is that the x's are IID samples from some distribution, which is fixed, but it's unknown to me, and it can be arbitrary. And the motivation for all that is that in real data of this type, there are settings where we don't know anything about the distribution of the data. And ideally, we would like to be able to handle noise even in those settings. So this is what distribution independent means. Now, the third and last term of the title is Massart noise. So let me explain what this means. So you observe your labeled examples, x, y. If y was, in the case of clean data, y would actually be the correct label of x, right? So now,
Mm-hmm.
what would be a reasonable model of noise? A reasonable model of noise would be that, okay, I take every y independently, and I perturb it, I flip it, I make it 0 from 0 to 1 or from 1 to 0 with some small probability, let's say 1/10.
Right.
Right? So this is what Massart noise is, but it's a little bit more subtle. What it tells you is that I take every label, and with probability at most 1/10, I perturb it. But you don't know what is the probability that I use to perturb it. It's a number that's less than 1/10, but it could be anything between 0 and a tenth.
Okay.
Okay, that's the definition of the Massart noise model. It means random perturbation, and the probability of perturbing every label is going to be bounded from above by some constant. Certainly, the constant should be less than a half, otherwise, I lose all information. And the feature of the model is that you don't know what the flipping probability is. It can be different across the examples that you observe.
Got it. And does that Massart Noise particularly model well some natural phenomenon that we see?
Right. So it's reasonable to assume that the noise added to the examples is independent or almost independent. But in general, we don't know, and certainly we should be assuming some boundedness, right? Otherwise, we get no information. But what we really don't know is we don't know if the same noise is going to be added to different examples. So in terms of practical applications, there are many. The people who defined this model, like in the 80s and 90s, have set out many settings where this is actually reasonable. So as a theorist, I just took the model and tried to analyze it.
Got it. Got it.
So let me tell you one thing that I think is surprising, especially if you haven't thought about this problem. Let's consider the case where you know a priori that every label is going to be perturbed with probability exactly 1/10.
Mm-hmm.
So is this model easier or harder than the one I mentioned already? So what would you think?
I would think easier,
Right?
but
Why
I
is
think
that?
you're going to say harder.
Actually, it's the opposite, right? So I would think that you would say that it's harder, but in fact, it's easier.
Oh, I guess I was thinking it's easier from I guess an information theoretic perspective. We have more information about the problem.
From an information theoretic perspective, when you have more noise, right, you can predict less accurately. So, but you are right in the sense that algorithmically, it was known how to
There's a
solve.
certain consistency
Right,
there.
right, right. So basically, when you know exactly what is the amount of noise you're going to add to every example, then in some sense you have the ability to invert the noise,
Mm-hmm.
right? So and in fact go from, let's say, the any statistic that is defined on the noisy data, there is a mathematical way to transform it efficiently to the same statistic on the clean data.
Mm-hmm.
So this has been studied a lot, like since the 90s. It has a name. It's called statistical query model. And there are some generic transformations that tell you that any algorithm that works in this statistical query model is actually tolerant to this type of noise. The type of noise where everything is going to be perturbed with the same probability.
Got it.
But the Massart noise model, where you know that the probability of flipping is going to be bounded from above on every example, at most 1/10, but you don't know what it is, even though the accuracy you can get is higher, information theoretically the problem is easier, algorithmically it's much more challenging. Because now if you see a given example with its label, you have no way of knowing if this label is 100% correct or 90% correct or anything between 90% and 100%.
Mm-hmm.
And this makes it really hard to actually invert. And in particular, this generic transformation I mentioned that relates this statistical query model with tolerance to noise fails to hold in the Massart noise model. So
Interesting.
we needed to do something new.
One more terminology or one more bit of terminology from the title is half spaces.
Right, right. Halfspace is just a linear separator.
Ah, got it. Got
Okay,
it.
just a
Got it.
linear
Okay.
model, right? So you have a bunch of points, you draw a hyperplane in Euclidean space. What's above the hyperplane is positive, what's below is negative.
All right. So, in order to analyze this, what kind of machinery did you call into play?
Right. So what we wanted to do is use SGD,
Okay.
right? It makes sense, right? Like, SGD is the most natural algorithm to use to solve an ML problem. So you need to formulate the problem in a mathematical way as an optimization problem. And let's say hopefully SGD is going to solve this optimization problem. And what we ended up showing as a first step is that this is impossible.
Okay.
Okay, so
Fundamentally, SGD can't be applied here. In other words.
yes, so this is like 50% of the truth. So if you try to write some kind of convex relaxation of the problem and try to solve it by SGD, this is going to fail completely. We can prove that, and the proof is not particularly difficult, right? But during sort of the process of developing this proof, we actually realized that even though SGD does not suffice to solve the problem of the entire space, it actually suffices to solve the problem on a non-trivial fraction of the space.
Okay.
Okay, so basically, I mean, this is of course it's a technical thing, but we showed that there exists a non-trivial fraction of the domain where SGD works. So this is an unknown subset that there is an efficient algorithm to actually detect. So we can find the subset of the domain where SGD works. We can solve the problem on that fraction of the domain and then iterate on the rest.
Mm-hmm.
Basically, the algorithm turns out to be an application of many calls to an SGD routine.
Are you able to either determine the importance of the subset of the space that you are able to apply SGD, or are you able to kind of keep track of how much of the space you've covered by iteratively searching with SGD?
Right, right. So to show that this algorithm is actually efficient, this process that I described, this iterative process, needs to happen a small number of times. Right?
Mm-hmm.
If it happens an exponential number of times, you haven't solved the problem efficiently. And this is part of the structural understanding that we obtain by solving the problem, but in every iteration, we actually cover a non-trivial, an inverse polynomial fraction of the space. After at most a polynomial number of iterations, we have covered the entire space. Right? Okay, let's say in every iteration we solve 1% of the problem. So we need 100 iterations to solve the problem.
Maybe this is a sidebar, but are there specific details of the implementation or the proofs that you or the what you covered in the paper that are accessible without getting too pulled into the theory?
I think the answer to that is probably no, but I'll be honest here. So it's not a terribly complicated paper. I think it's
Uh-huh.
actually I think it's actually quite simple from a theory perspective. It has something original that people didn't come up with before. So what I maybe should say that this, even though it answers an open problem from a long time ago. So this was posed in the 80s in learning theory. It's not over here. So this is in some sense the first paper in this sort of line of work of doing distribution independent learning with noise, and I believe it's going to lead to many developments. In particular, like something that we have been able to answer very recently with a colleague, with one of the co-authors of the same paper, my colleague Christos Zamos, and two of our PhD students here at Madison, is that in fact, if we make some very weak but still reasonable assumptions about the distribution. So if we look at the distribution specific setting, but still reasonable, we have a way of showing that SGD actually works as is. So we relax the problem a little bit, but still in a way that it remains reasonable, and we can now solve it by SGD.
And you're a bit cagey about the assumptions that you're making. Are you fixing to a limited subset of known distributions, or is there some other
Right, right.
quality about the distributions that's important?
Right. So the paper is going to be online in a week, so I'm happy to share this. So, I mean, the terms are going to be sort of potentially a little bit technical, but really what we need is that the distribution of the inputs is reasonable in the sense that it's not too concentrated or too sort of, like, let's say, not too dense or not too empty anywhere.
Okay.
Okay,
And
so there are these technical terms that are called concentration, anti-concentration. So as long as we have weak properties of that form, these properties suffice to solve the problem.
okay. Interesting. And so, what is it about this paper that you think kind of caught the interest of the NeurIPS reviewers and landed it the Outstanding Paper Award?
Right. That's difficult for me to answer. I mean, this is, I'm happy that the paper got recognition, and I really believed in it before we submitted it. So I believe it was a significant advance. I think the reason is because it solves, like that's my guess, that it solves an old open problem and recognized open problem in machine learning theory. Really, essentially, no progress had been made on distribution-independent learning in the presence of
Mhm.
noise for a long time. And also, at the
Mhm.
same time, the solution turns out to be quite clean, at least compared to other theory papers.
And were you surprised by how clean it ended up being?
Yes, I was very surprised. In fact, we solved this problem in a month, and then we spent like 10 months to improve it, and we couldn't. Right, so it somehow gives me the belief that this turns out to be this is probably the best possible solution to the problem.
But yet you remain convinced that there's more to come, and you'll be able to build on it or improve on it.
Yes. I mean, there are some other things that we have recently done, and I am indeed cagey about them because they're not sort of written yet. But yeah, I believe that this line of work is going to lead to a lot of progress in the next couple of years.
And so, for folks that are interested in digging in a little bit deeper, there's obviously this paper, but you've also recently co-authored a survey on this broader space. Can you talk a little bit about that and the focus there?
Right. So since this initial 2016 paper on robustly learning high-dimensional distributions, so we're back in the unsupervised setting. So once we wrote this paper, a number of people found this interesting, and at this point there is a long literature on algorithmic high-dimensional robust statistics. So what I did with my longtime collaborator, Daniel King, we decided, okay, there's so much work in the past 4 years, and it's unclear if people understand other people's work, so let's write a survey giving an overview of all the techniques that people have developed in this space, what are the problems that have been solved, what are the problems that are open, somehow giving some kind of pause, like a point where the community needs to say, okay, this is what we have achieved so far. What are the next directions to look at? So this is available on the archive, and it's also going to be sort of at least a short version of it is going to be part of a book chapter on beyond worst case analysis that's going to be published by Cambridge University Press soon.
Okay, and this is the recent advances in algorithmic high-dimensional robust statistics that was published on arXiv back in November of last year.
That's right. That's right.
And how many papers does it cover?
I mean, in true detail, probably around 15, but we give an overview of about 100.
Oh, wow. Wow.
There has been a lot of work in this space in the past few years, and really the reason for that are these theoretical questions have the potential of practical impact, and already we have seen some steps in that direction. For example, one of the prototypical applications of robust statistics is in something that's called data poisoning. So this is a phenomenon where you have a machine learning system. So the input coming from the outside, let's say you have many users, but then you have a small number of malicious users that are trying to insert fake data in the system and completely destroy the behavior of the system. So a robust algorithm would actually be able to prevent that. Okay, so we have had a number of papers, and I've co-authored a couple, where we actually do that. We actually show that some of these theoretical algorithms developed in these initial works can give you provable and practically useful defenses against these types of data poisoning attacks in machine learning systems.
Okay. And are you aware of any actual implementations of the work in this space?
Implementations in what sense? I mean, I'm referring...
in a sense of a company using it.
I see. Okay, so yeah, we're not there yet. So I'm very eager to sort of to collaborate with people to do that. At this point, we're at the stage where we have sort of proof of principle experiments published in like ICML and NeurIPS. So we're not yet at the stage where this sort of line of work has reached the industry. But it's a goal for the immediate future.
And do you think that is because it sounds like folks are aware of the problem? Are the solutions sufficiently generalizable at this point that they are easily applied in industry?
So I think the reason is that it hasn't propagated enough, okay. Right? So in some sense, another reason might be that some of the algorithms are not just gradient descent. Okay, they're a little bit more sophisticated algorithms using spectral methods. They're not as automatic as machine learning people would like them to be. Mm-hmm. So basically, a next step, which is something I'm currently working on, is actually completely eliminate the algorithmics from these problems. Actually formulate them in a certain way so that we can just use SGD and solve them. And somehow the insights obtained from these initial papers are useful to achieve that. So let me point out that these problems are inherently non-convex. And this is why they're so hard. Okay, mm-hmm. But even for non-convex problems, when they have some additional structure, it is quite possible that if you formulate them the right way, some version of SGD actually solves them. Okay, and this is something that I believe is true, and we're working towards proving it.
Well, Ilias, thanks so much for taking the time to share what you're working on.
Sam, thank you very much for the opportunity that you gave me.
Thank you. All right, everyone, that's our show for today. For more information on today's show, visit twimlai.com/shows. As always, thanks so much for listening, and catch you next time.